Hello, I'm Isabela Fernandez, and welcome to my lab number 2 of Physics 2211 of motion of a falling object. Introduction. To start off, I want to explain the purpose of this lab. We were to observe the motion of an object that is dropped from rest and falls straight down, analyze the video in the app of Tracker to extract the object's position and corresponding time, then create computational models with the app of GlowScript and based on the physics principles that apply to this scenario and model the effect of the drag force in the object's motion and compare both models to arrive to conclusions. So the problem and hypothesis of this lab. The problem and the question is, will there be a difference between an object falling when the drag force is being considered versus when it isn't? That is to say, which computational model will be more accurate to the observed model. So my hypothesis is that the model that includes the drag force will be the most accurate model, and it will resemble the observed motion because it is taking into account more forces act on the system. That is to say, the model that includes drag force is accounting for gravitational and drag force versus the other one that is only including the gravitational force applied. The fundamental principles involved in this lab is Newton's second law of motion that describes the motion of an object produced by unbalanced forces, and that the net force acting on an object is equal to the product of its mass and acceleration. Since we know this, we can arrive to the conclusion that the change in momentum equals F net times change in time. We also use the drag force, which is the force acting opposite to the relative motion of any object moving in the system, and we have the equation labeled too. The gravitational force is the force of attraction between all masses. 2. Tracking observed motion. Using the app of Tracker, we were able to record the observed motion of the pillow and how it dropped vertically down by labeling the axes, which are in purple, and the points of mass in each time frame, which are in red. Here is further elaboration of the observed motion by a graph, and we can see here the time frames and each position in the y direction tracking the predicted motion. So now using the app of GlowScript, we were able to predict the motion of an object without drag force, and we can see how the object moves directly vertically as well. Here we can see the predicted motion of the object without drag force in another graph, which was extracted by the data using GlowScript. So an explanation of the GlowScript code used for the model with no drag applied. We can see here that the proportionality constant for the magnitude of drag force is 0, and that the F net applied to the system was just the variable of negative gravity times the mass of the ball times the vector of j hat, which is just the unit vector for the positive y-axis pointing up. Also, using GlowScript as well, we were able to predict motion with drag force, and we can see how the position time graph here varies from the one without drag force. And here is another table and another graph using Excel that also shows this. And the explanation of the code using drag force is that the proportionality constant for the magnitude of the drag force will now be greater than 0, meaning that it will affect the system, and F net will now include the gravitational force and the drag force. Analyzing and comparing motion. So here we have the observed versus the predicted motions all laid together. We can see that the observed motion is in blue, and the predicted motion that includes the drag force further resembles that one in blue, which means that it's the most accurate and closest to the observed motion. And you can see how the predicted motion, that one that has no drag force, is further apart and it's steeper down than the predicted motion with drag force. So basically what I mentioned was the analysis and the interpretation of the data, but we also need to account for errors made on the lab experiment that were not accounted for in the system. For example, the reason why the predicted motion with drag force is not the same as the observed motion is because there are still other forces that were not accounted for, like the air resistance or wind in the x direction, since we're only looking at the y direction, that could have altered the system too. In conclusion, what does this mean? The model that predicts terminal velocity is a model that includes both gravitational force and drag force because it is the most accurate representation of how the system actually looked. Also, terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. So this means that the net force is actually zero because the forces are canceling because they're balanced. We can also ask the question of what if the object was initially thrown downwards, but actually the terminal velocity would not change because if an object is thrown at 0 meters per second and at an initial velocity, both slopes will still flatten to the same amount even if they started with steeper slopes to begin with.